So moving to D and F block elements. Ready? Actually the D and F is from the names of subshell. So usually it is in a small letters. Okay. I know how to write the capital letters, but it is actually in a small letter. That's the logic. Okay. So leave it ready. So because the are usually using small letters and shell names are by capital letters like K, L, M, N shell, S small, SS, PDF like that are small letters. Okay. Anyway, first of all we can discuss the D block elements. D block elements. Okay. Were lot of and two important compounds like K2CR and MnO4. Ready? Fine. So let me introduce the D block element. You know there are 40 D block elements, what we called as 3D series. Okay. First point. Okay. First point. Last electron enters to. Element is a element if and only if the last electron is enters to penultimate D subshell, right? What do you mean by penultimate? Just inner of the outer, or second last one. Okay. Last electron goes to penultimate D subshell. Ready? D block element. First point. The last electron enters to penultimate D subshell, in bracket n-1d. Penultimate D subshell means n-1d. Okay, you know the meaning. Okay, this is the nth shell, n-1th, n-2th. Okay, the nth one is said to be ultimate shell. n-1th should be penultimate, whereas n-2th known as anti-penultimate. Your F block elements are belongs to, or F block elements where the last electron enters to anti-penultimate subshell. Okay, that's a common knowledge. Okay. So last electron enters to penultimate D subshell. Ready? If the last electron is enters to the penultimate 3D subshell, they are belong to 3D of how much? 10. Scandium, titanium, vanadium, chromium, manganese, copper, zinc. Okay. 30. Okay. Actually this is of group third group. Ready? Up to 12th group. Okay. Usually they are discussed in a horizontal pattern. Okay. Fine. And next, this is also known as first transition series. First transition series. Okay. What about the next 4D series? What are the elements? Yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, gold, silver, cadmium, and this is from 38, 48, where the penultimate D subshell is 4D. Okay. Yttrium, zirconium, niobium, molybdenum. This is Tc. Technetium, ruthenium, Ru, rhodium, Rh, palladium, Pd, silver, actually argentum. That's a Latin name. 5D series. 5D series, which starts from lanthanum. Okay, the atomic number of 57. Then the lanthanoids. Then the lanthanoids of 14 elements, followed by your hafnium with atomic number 72. Ready? From 58 to they are from cerium to lutetium. Okay. Hafnium, tantalum, tungsten, rhenium, osmium, iridium, platinum, gold, mercury, were mercury of 80. Lanthanum, hafnium, tantalum, tungsten, rhenium, osmium, iridium, platinum, gold, mercury. Okay. And this is a 5D series, or this is second transition series. This is third transition series, or the last one, fourth transition series, or otherwise known as 6D series, which is from actinium. Actinium of 89. Okay, wait, 89, followed by rutherfordium of 104. So there is a 90 to 103. The elements are actinoids: thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, like that. Okay, up to lawrencium. So here we ready. Rutherfordium, then dubinium, then seaborgium, borium, hassium, meitnerium, tungstatium, rhodium, copernicium. Well, copernicium is 112. Copernicium is 112. Okay. Ready. So these all are the elements, simply or D block elements, consist of 4 into 10, 40, right? 4 into 10, 40 elements are there. Ready. And their general electronic configuration, general electronic configuration, what it is? N-1 D 1 to 10, NS 0 to 2, NS 0 to 2. Okay. Okay. Usually the other groups are discussed in a vertical pattern. The properties are discussed in a vertical pattern, not in a horizontal pattern. But here the properties are discussed in a mostly discussed in a horizontal pattern. Why means their outer electron is always same, right? Listen, I have scandium. Scandium, the electronic configuration is 3d1, 4s2. I have vanadium, the electronic configuration, scandium, titanium, vanadium, 3d3, 4s2. Where the outer electron is already filled, 4s2. Okay, the next electrons are enters to a inner shell. Okay, so they have comparatively similar property. Since their outer electron is already 4s2, right? Okay, then they differ in what? They all have 4s2. Generally they all exceptions are there. Okay, they all have 4s2 generally, right? Okay, but they differ in this is having 3d1, this is having 3d2, 3d3. Okay, they only differ in what? Inner electrons, but the outer electron is same. So that's why they all have same kind of what? Property. That's why they are discussed in a horizontal pattern. Whereas in the case of p block element, listen, I have a p block, I have a set of p block element, say have aluminum followed by what? Aluminum followed by silicon followed by phosphorus. Where the electronic configuration 3s2, 3p3, 3s2, 3p4, 3s2, 3p5. Where the outer shell electron is entirely different. Their properties entirely different. So they better to study in a vertical pattern. Okay, whereas in the case we are usually in a horizontal trend. Why means their outer electron is same and they all are different inner electrons. Okay, fine. So there are a lot of exceptions, just a point. Okay, copy that point. They are also known as transition elements. They are also known as transition elements. Why they are also known as transition elements? Why they are said to be transition elements? Because they brings the transition of metal S to non-metal P. Okay, if we are moving through the periodic table from left to right, what happens? The metallic character become a non-metallic character. Ready? Where that transition, that change is brought by transition elements. So they are simply known as transition series. Okay, so they are also known as transition elements. In bracket have a small reason. Due to transition from metal S to non-metal P, due to a transition from metal S to non-metal P, metal S to non-metal P. Ready? Metal S to non-metal P. Okay, metal S to non-metal P. Ready? One more point. They are studied in period wise. They are studied in period wise. Right? They are studied in a agreed, not in a group pattern. Studied in a period wise. That the reason is nothing but their outer electron remains same, where only the change is for inner electrons. Okay, they are studied in a period wise. In bracket have same outer electrons, same outer electron ns2, same outer electron ns2, and different inner electron. Why they are discussed in that pattern means they all have same outer electron ns2 and they all differ in inner electron. That's the reason. Okay, that's the reason why they have similar type of property. These all have a same type of property. So there are some exceptional configurations are there. Okay, so exceptional configuration. In your 3D series, it is for chromium and copper. So chromium, what is the configuration? 4s1, 3D5. For copper, the real configuration 4S1, 3D10. 3D10. Okay. Oh, sorry. This is not copper. Okay. But there are lot of exception in your second transition series. And it's from niobium itself. Niobium have exception, molybdenum have exception, ruthenium have, rhodium have, palladium have, silver have. These all have exceptions. Okay. The configuration of niobium. The expected configuration is 4s2 3d3. Actually 5s1 4d4. 5s1 44. 5s 44. It is given in your textbook. Okay. Molybdenum 5s1 45. Okay. Followed by ruthenium. Ruthenium have 5s1 47. Ruthenium followed by rhodium. Rhodium have 5s1 48. Followed by palladium. Palladium is entirely different. 5s0 40 10. 5s0. Palladium shows 5s0, ns0. Okay. Then silver is something like your copper. 5s1 40 10. 5s1 40 10. So there are a lot of exceptions there. Okay. The next exception in 5D series is actually 4, not 4. In 5D series 4, tungsten, platinum and gold. Listen, actually for only platinum. Okay, sorry, the change is only for, listen, tungsten the configuration is, the expected configuration is, what is the configuration of chromium? 4s1 3d5. Molybdenum 45. So the expected configuration for tungsten 6s1 5d. So it is actually 6s2 5d4. Because there is no exchange for stability. So that's the exception. That's actually the real case. Ready? But that's an exception from our expectation. Okay. This is a usual case. Ready? ns2 n-1 d4 is for the usual case. But we know that this is for what? This is for stability. But that effect is not observed here. Okay. The reason is the reason for the exception configuration is not only the stability. There are some kind of reason also. Okay, shielding effect, say electron-electron repulsion. Okay, exchange energy, exchange possibility. So there are a lot of another reasons for this exception configuration, not only the stability. Right? So our expectation is not here in case of tungsten. Ready? So tungsten 6s2 5d4, whereas platinum is 6s1 49. That's an exception. 6s1 49. I'm sorry, 5d9. 6s1 5d9. Gold, the usual. Gold is like copper, silver, usual exception. 6s1 5d10. Okay. Tungsten is not actually an exception. Okay, it is an exception from our expectation. Okay, we have an expectation like this. Ready? From that there is an exception. Since the configurations are given in your textbook, in your NCERT updated version, there is the configuration of fourth series also. Okay, so in fourth series, the exception is only for Rongenia, as usual except. Okay, Rongenium, gold. What it is? 7s1, 6010. Okay, no other one have any exception. Fine. So that's all about the electronic configuration. Ready? So these all are exceptions. This is given in your textbook. Write a point. The exceptional configuration may be due to stability, nuclear attraction, screening effect, inter-electron repulsion, etc. Okay, so we can't give a well explanation for all this stability. Okay, some of them can be explained in terms of your stability. There are a lot of another factors, depends what the exceptional or there are a lot of another factors for this exception. Okay, not only stability, keep it in mind. Ready? Fine. So next important point, element is said to be transition element if and only if, that is the actual definition of transition element. An element is said to be a transition element. I think you are familiar with that. Zinc, cadmium, copernicium, like that, they are not belongs to transition elements. Why? They should, element is said to be transition element if it have a partially filled d orbital in their ground state or in a common oxidation state. Okay, the common oxidation state of 12th group is +2, whereas 11th group is either +1 or +2. Okay, so these all are not belongs to transition elements. Why means? What about the configuration of that all category? Configuration of 12th group? 12th group generally NS2 N-1 D10. Okay, so what about this is a ground state configuration, agreed? Normal ground state configuration of 12th group is NS2 N-1 D10. Ready? What about the excited state configuration? Excited state configuration means the configuration +2. These two electrons are loosed. So NS0 N-1 D10. Ready? So the possible electronic configuration of 12th group elements in their ground state or in their excited state where N-1D or the d orbital is fully filled. So there is no partially filled d orbital. So actually they are not belongs to transition elements. Okay, that's why their properties are entirely different. That is, they all are not actually tough, not strong. Zinc, cadmium, mercury are volatile metals actually. Okay, volatile. They are soft metals, volatile metals. Comparatively compared to this one. Why means their character is entirely different. Okay, due to fully filled d orbitals, they can't participate in metallic bonding like that. Okay, metallic bonding, covalent bonding. So their toughness is relatively low, or their strength is relatively low. Okay, so they shows a lot of exceptional character from the rest of elements. So actually they are not considered as transition elements. Okay, so first of all you have to keep the definition. Ready? Definition. Definition. An element said to be transition element if it have an element said to be transition element if it have a partially filled d orbital in ground state or any common excited state. Partially filled in ground state or common excited state. Common excited state means common oxidation state. Okay. Ready? Idana a definition. This is the actual definition. Okay. So definition. Listen. Based on the definition, so write a point that is 12th group elements. Like 12th group, what are they? Zinc, cadmium, mercury, copernicium, not considered as transition elements. Okay, because ground state configuration N-1 D10 NS2. Okay, fulfilled, right? It is fulfilled. Excited state configuration, excited state is +2 or the configuration is N-1 D10 NS0. Till now it is what? Still it is fulfilled. So they are not belongs to transition elements. Okay, but what about the group 11? The group 11 can show the oxidation state of +2 or +1. That's the common oxidation state. Cu plus, Cu2 plus, like that. Okay, but 11th group, what are they? Copper, silver, gold, rhodium, like that. Okay, considered as transition elements. Okay, reason? The configuration of +2. What is their general electronic configuration? They all general electronic configuration, right? NS1, N-1, D10. Oh no, NS1. What is their electronic configuration? N-1, D10, NS1. So if they are in +2 means N-1, D9, NS0. So one, two, three, four. Here is a partially filled. Okay. So we haven't have a partially filled d orbital in their +2 common oxidation state, so they can be considered as transition elements. Ready? But in the case of group 12, they can't form a partially filled d orbital in their any state, or in their ground state or a common oxidation state. So they are not considered as d block transition elements. Okay, fine. So that's the explanation. So that's the point which is mentioned in your textbook. Listen, and these elements are also known as coinage elements. Coinage elements. Okay. Ready? So next we are moving to the important properties. The first property, atomic size. Atomic size. Okay. So this is okay. Ready? Why the 11th group considered as transition elements? This is the reason. Why the 12th group? This is the reason. Okay, fine. The next property, that is atomic size. Atomic size. You know the atomic size, which is a fact. Atomic size is classification of elements. Is it over? Fine. So what about the dependency of atomic size with respect to effective nuclear charge? Atomic size is directly proportional to effective nuclear charge or inversely proportional to effective nuclear charge. If the effective nuclear charge, what do you mean by effective nuclear charge? Nuclear charge which is after the consideration of screening effect. Screening effect. You are familiar with the screening effect? Are you familiar? What do you mean by screening effect? So shielding of inner electrons to the outer. Okay, listen. I have sodium, atomic number 11. So the actual protons is 11 proton. So I know the nucleus have what? 11 proton surrounded by shells. Simply this is the last electron, right? Okay, so my expectation is 11 protons are attracting this electron. My expectation, and that is said to be nuclear charge. Simply the real nuclear charge. But we know that there are what? There have inner electrons. Inner electrons which act like a screen or shield. Ready? There are inner electrons which act like a shield. So after this screening, a reduced nuclear charge will be affected on this electron, right? After the screening, a reduction or reduced nuclear charge will be effective to this electron, and that charge is actually called effective nuclear charge. Okay, actually the 11 protons are not attracting this electron. Some attraction is cancelled by agreed. The screening effect by inner electrons. Okay, so a charge which is always less than 11 proton will be attracted here, and that real charge, what it is called as effective nuclear charge. Effective, or that effective nuclear charge, we know it is represented by Z star, and Z star is Z minus sigma, where sigma is Slater screening constant. Okay, so there is a difference between nuclear charge and effective nuclear charge. Nuclear charge means simply it is actually the charge offered by nucleus. Effective nuclear charge means the actual or real charge which is effective on the upper electron. Okay, so the effective nuclear charge increases, what happens? The size. What about the screening? If screening increases, attraction reduces, right? If screening increases, attraction reduces. Attraction reduces means more atom will be expanded. Okay, so size increasing. So this is a relation. Agreed? As screening increases, atomic size decreases, whereas effective nuclear charge, effective nuclear decreases, atomic size increases. Fine. This is a relation. So you have to know this relation, and this is discussed in your classification of elements. It may discuss in your classification. Now, my point is, from left to right, in a particular period from left to right, the size, first the size from left to right, from left to right. My property is atomic atomic size or atomic radius, okay, from left to right, which means across period. What is the trend of atomic size and what is the necessary explanation? Okay, listen, left to right, what happened means size decreases initially. First it decreases, then remains constant. Okay, first the size decreases, then the size become a constant, finally a small increment. Okay, finally increases. So what will be the reason? What about the first case? In the first case, as electrons, scandium, titanium, chromium, manganese, iron, cobalt, nickel, copper, like that. Okay, so as electrons say as moving from left to right, what happen means nuclear charge increases, but the screening is not much effective because electrons, here it is 3d 1, 3d 2, 3d 3, inner electrons are coming, so there is no screening. Okay, once saturation, inner electrons have a particular number, then the screening is effective. Initially the number of inner electrons is less. Ready? Once electron crosses 5 or something like that, then only their screening is effective. Okay, this is competition between what? Nuclear charge and there is a competition between nuclear charge and screening. You know that from left to right, nuclear charge increases, right? Nuclear charge increases. As nuclear charge increases, what happens? Nuclear charge increases, should be decreases. This is a usual reason, or this is observed in all case. But here, initial size decreases, finally have a small increment. Okay, so there is a competition between screening and effective nuclear charge. As from left to right, nuclear charge increases, no doubt, increases by 1 unit. Okay, in addition to that, inner electrons are also increasing. 3d1, the inner electron is 1. 3d is inner orbital, right? Inner electron 2, inner electron 3, inner electron 4, inner electron 5. So what happens if the number of inner electron increases? The screening will be effective. Agreed. The outer is what? Outer electron is always 4s2. Ready? As we are moving from left to right, the number of inner electrons increasing. So the screening will be effective. So both screening and nuclear charge increase when we are moving from left to right here. Ready? Both are increasing. So if screening increases, what happens? The size have a tendency to increase. At the very same time, if effective nuclear charge increases, what happens? Size have a tendency to decrease. So there will be a competition. Ready? I think it is okay. When we are moving from left to right, what happens? The number of proton increases means nuclear charge increases. Ready? So there is no doubt when we are moving from scandium to zinc, nuclear charge increases, atomic number increases, protons increases. As nuclear charge increases, what happens to size? Size decreases. Okay. But here one more problem is there. The coming electrons are inner electrons. Okay. So as they are inner electrons, what happens means the effective screening also increases from left to right. Okay. The screening have a tendency to increase the atomic size, whereas nuclear charge have a tendency to decrease the atomic size. Then there will be a competition between them. Okay. Initially the number of low. Ready? So screening will be low. So which dominate? Effective nuclear charge dominate initially. So initially number of inner electron is comparatively low. So nuclear charge is increasing. So effective nuclear charge dominates. So what happens? Nuclear charge dominating means size decreasing. That's why initially the decreases. Okay, initially the size decreases. The reason is effective nuclear charge greater than with the effect of due to effective nuclear charge is greater than what? Screening. Okay, but once it become a 4d5 or 3d5 like that, okay, in a middle position the number of electron increases, moreover consequently number of electron and screening effect increases. Both are increasing in a correct pattern. So screening effect increases the size, whereas in the very same time effective nuclear charge decreases the size. So one try to increase the size and one try to decrease the size. So it become a constant. Okay, seems to be a constant. Ready? So then remains a okay, finally the size is increased. Why? It is actually due to electron-electron repulsion. Okay, once the shell is completed, there may be an electron-electron repulsion, you know. Okay, here 3D1, 3D have a space for 10 electrons. Here 3D1, 3D4, 3D5, 3D6, 3D8, 3D9, 3D10 is the maximum capacity. Okay, from 3D9, 3D10, what happens? Electron have a repulsion because it is a crowded one. Ready? The shell can accommodate maximum of 10 electrons, where presently it is 9 or 10. So there is an electron-electron repulsion. So it may expand. Okay, or the other reason is screening increases. Okay, the main reason is what? Repulsion, and we can also say number of inner electron increased. Okay, so both have a counter effect to increase the size. And this is the explanation. Okay, so we can say that screening increases and electron-electron repulsion increases. So this is a general trend of size for any transition series. Okay, and this is a necessary explanation. Ready? Fine. So first of all, copy this one. Ready? Then you can show that. Okay, there is a figure which representing the variation of size in your textbook. What do you say, madam? Down the group size increase or decrease? This is 3D series. Okay, this is 4D, this is 5D. So here the increment of size. Okay, here from left to right. Okay, so what happens? All have a general property. Left to right. From left to right. Listen, the size first decreases. Just on increasing. Ready. 3D, which is less than what? 4D. Which means 3D, 4D, 5D. Down the group size increases. Okay. Is less than 4D, but the size of 4D and 5D nearly. I think you know the reason. Lanthanoid contraction. So just plot this one. Lanthanoid contraction. The reason is lanthanoid contraction, and the general trend is first decreases, then approximately a constant, finally increases. Okay, and why the size of why there is no much difference in the size of 4D and 5D means it is due to lanthanoid contraction. Okay, next some more points add here. In D block elements, largest atomic radii for lanthanum and smallest for nickel. Okay, largest is for lanthanum and smallest is for nickel. Ready. Next point, due to lanthanoid contraction, the size of ZR and HF, zirconium and hafnium, ZR and HF, comma, the size of ZR and HF, comma, technetium TC and RE, ZR and HF, comma, TC and RE, comma, TA and NB, tantalum and niobium, comma, RU and OS are nearly same. Okay. The next, ionization energy. Ionization energy. Usually ionization energy from left to right increase or decrease? Ionization energy from left to right increases or decreases? Increases. Here also increases, but not much increased. Okay, the ionization energy is a factor that depends on what? Size, nuclear charge, screening, like that. Okay, or simply nearly size. Okay, since they all have a similar size, okay, or the size have a lot of variation, sorry, not much variation, not have a much, Normally from left to right the size is gradually decreasing. Okay, so it is difficult to remove an electron from that atom, which means ionization energy increases. Okay, but in case of d block elements, size have not much decrement, or size is initially same. So initial and final is nearly having a similar size. Okay, first decreases, then constant, finally just increases. Okay, and these all have similar size. Middle ones all have similar size. So there is no considerable change in size. Therefore, ionization energy generally increases from left to right. Ready, but the variation is not much. Okay, small changes. Although the successive members have small difference in ionization energy, neighboring members have small difference in ionization energy. Ready, increasing from left to right, that is okay, but the neighboring members, the difference between the ionization energy is considerably small. Why means due to the size. Okay, so that is the point. Next, atomic size, ionization energy. First point, they have increase in ionization energy when moving across a period. Have increase in ionization energy when moving across a period. Ready, moving across a period, but the difference of IE between successive member or neighboring member low. But the difference of IE between neighboring member, difference of IE between neighboring members low. Okay, write the reason in the bracket. Due to similar size. Okay, due to similar size. Ready? In 3D series, the ionization energy, the IE of zinc and manganese are relatively high. In 3D series, the IE of zinc and manganese are relatively high. Reason? Zinc have 3D10 configuration, whereas manganese have 3D5. Bracket due to stability configuration. Due to stable configuration. Due to stable configuration. Due to stable configuration. The next, put it as a question. Put it as a question. Second ionization potential of chromium and copper higher than second ionization potential of chromium and copper higher than their first ionization. Higher than their first ionization. Okay, reason? Reason? Chromium the configuration 4s1 3d5. Removal of first electron Cr plus, and this is IE1. Ready? So the configuration will be 4s0 3d5. Removal of second electron, that is IE2. It become Cr2 plus. So 4s0 3d4. Okay. So the reason is nothing but the removal of second electron from copper and chromium disturbs the stability. Okay, disturbs the stability. So that's why have an exceptional high ionization energy. Removal of second electron, put it as answer. Removal of second electron for copper and chromium decreases the stability. Removal of second electron for copper and chromium decreases the stability. Decreases the stability. Decreases the stability. Okay, that's right, sir. Ready. Next term കൊടുക്കാം. Ionization energy NCERT ൽ തന്നെ പറയുന്നുള്ളൂ. Next term കൊടുക്കാം. So if the questions are like that, why the ionization energy of this one is greater than that one, so you simply consider the stability of configuration, then you may have a satisfactory explanation. Okay, fine. So next the term density. Okay, density is a factor that depends on what? Atomic radius. Density means what? Mass per volume. Ready? So as size increases, what happens? Our radius increases, volume increases, density decreases. Okay, so what about the size of S block and D block elements? From S block to D block element, what about the idea? What is the idea about size? Size decreasing, so density increasing. So the first point, density, the first point, have high density compared to S block elements. Have high density compared to S block elements. High density compared to S block elements. Just a reason bracket lo place here. Reason size less compared to S block. SLA size less compared to S block. Okay, when I bracket reason size comparatively low ആണ് S block in. So this is explanation. Okay, ready. Next point, osmium and iridium. Osmium and iridium have high density. Osmium and iridium have high density in D block elements. Ready? Next point, in density size ന്റെ ഓർഡറിൽ തന്നെയാണ് ഏകദേശം മൂവ് ചെയ്യുന്നത്. ഫസ്റ്റ് ഡിക്രീസ് ചെയ്യും ആ ഓർഡറിൽ തന്നെ. ദാറ്റ് ഡിക്രീസ് ചെയ്യല്ല, സേ സൈസ് that depends on size. Okay, density that mainly depends on size. So next point I do in across a period okay, density increases first, okay, then remains constant, finally decreases. Reason? That is the inverse trend of what? Inverse trend of size. From left to right, size initially decreasing, which means volume decreases, density increases. Okay, so inverse trend of your size. Ready? So now next point. In 3D series, copper have low density. Copper have high density and scandium have low density. Okay, from scandium to, listen, scandium, titanium, vanadium, chromium. Density, first density, size first decreases, so density increases. Okay, then manganese, iron, cobalt, nickel. Okay, up to this one remains constant. Remains constant means nearly constant. There is a small increment. Okay, finally size increases, which means density decreases. Okay, so the density of zinc that is less than, finally decreases, so the density of zinc that is less than copper. So copper having high density, ready, whereas scandium having low density. That's the point. Ready? In a 3D series angane consider. Next, down group. What about the density of 3D and 4D? 3D, 4D, 5D. Down group size, what happens to size? Down group size increases, automatically density decreases. So first point, the density of 3D is less than 4D. Why? Why? Density is a term that depends on what? Size, not only the size, but also the mass. Okay. Across a period there is no, listen, across a period there is no considerable change in mass. Okay. So we can compare the size. Is it okay? But down the group, what happens? Down the group, there is a considerable change in mass, considerable change in atomic number, mass. Okay, so down group, what happens? Mass increases. Mass increases means density also increases. So relatively, the mass factor dominates. Okay, hence density increases. But from 4D to 5D, density nearly double. Density nearly double. The density of 5D is nearly double that of 4D. Why? Why? Listen. From 3D to 4D, the density is normally increasing. Okay? Because 3D to 4D, the density normally increasing. Density is actually what? Mass per volume. From 3D to 4D, what happens? 3D to 4D, what happens? Mass increases, okay, but size decreases, but the mass factor dominates. Ready? So density increases in a normal way. But what about the 4D and what about 4D and 5D? Listen. Comparing 4D to 5D, you know there is a lanthanoid contraction. There is a lanthanoid contraction, which means the size, there is no increment in size. Is it okay? The size of 4D and 5D are nearly same due to lanthanoid contraction, but there is an increment of mass. Is it okay? So fine, density is equal to mass by volume. Comparing 4D to 3D, mass increases, but this remain constant. So what happens? Have a greater increment in density. Okay, that means nearly doubled. Here there is a, from 3D to 4D there is a gradual increment, normal increment. Y means mass increases, so density may increase. In the very same time, size increases, so density may decrease. Okay, so the factor size try to decrease the density, the factor mass try to increase the density. So there may be a competition where the mass factor dominates. So there is a normal increment of density. Ready? But where in the case of 4D to 5D, the mass having an increment where the size have no increment. Ready? So the dominating factor is always mass. Size have no change, which means size have no role. So this have no role. So as mass increases, no doubt mass increases, so density increases. Okay, so that is the trend on moving down the group. Ready? But across a period, we can compare the density using what? Volume. Because mass have no considerable increment. 1 unit atomic number increase here, so mass have not much increment. But down the group, mass have a greater increment. Okay, so that down the group, the density factor that depends on mass also. Okay, so the point, what is the last point? The density of 3D series, 3D is less than 4D. The density of 3D is less than 4D.
So copper the high density, then scandium low density. Copper
density increase from left to right? So then remains a constant. Then remains constant means there is no mass. Okay. In 3D series, copper have high density. What is written in your note? In
copper have high density.
High density and scandium have low density. Fine. In 3D series, the element with the, what about the order of size? Size. Across a period, size is the dominating factor, right? Okay. For considering density, you can consider the size. Size decreases, constant, then increases. Okay, so listen, decreases, then become a constant, finally increases. So most decrement is for, I think this one, decreases to a particular value, okay, then finally increased. So the end member in the decrease is copper. Okay, so relatively, and smallest one is nickel. That is already written. In D block elements, the largest size is for lanthanum and smallest one is for nickel. Okay, so this means that it's decreasing to here the decrease, that means the remains a constant. Decrease to an extent. Finally, there is a small increment. So these two are having small size. So relatively their density is high. Okay, density high, whereas this one have high size. The size is decreasing. So scandium have a greater size. So the density will be low. Okay, so scandium have low density and copper have high density. This is actually experimental studies. Okay, this is perfectly on the basis of gram per cc value. So we can have some theoretical explanation. Ready? So here the explanation. This is period. Now down the group. Down the group or simply down the group. The density of 3D is less than 40. The density of 3D is less than 40. Reason? This is the reason. Okay. This is the reason. You can show the reason. 3D to 4D. Mass increasing. Okay. Size I'm sorry, size increasing, I'm sorry, size increasing, okay, but which dominate? This increment of mass dominates, so there is a net increment of density. Okay, size tend to decrease the density, okay, whereas mass tends to increase the density. Where mass dominate means, so there is a net result of increment in density. Ready? So from the next point, from 4D to 5D, density nearly doubled. From 4D to 5D, density nearly doubled. Okay, density nearly doubled. Nearly doubled. So there is a high increment in the explanation. Density doubled. The reason is that from 4D to 5D, mass increases, size nearly same on due to lengthened contraction. So greater, so there is a greater effect of mass. So greater effect of mass means a greater effect in density. So density observed to be double.